registered birth. Like, you don't have it now, like, little ship years and other stuff. But it was still.
How was the movie?
I learned the ones I didn't watch.
We might end up watching, I mean, so I have those, I have a bunch of those. I have like, well, each DVD has 3 on it, 3 shows on it, and I have 10 DVDs, so I've got 30 shows. So anytime lab comes up and the weather's not cooperating, I'm going to throw one in, because, you know, we get to learn something without, there's more of it that we keep learning. Was the test about the right length?
Yeah. That's right.
It was shorter than I expected, honestly. But that's a good thing.
That's a good thing? I told you how long this is going to be.
Oh yeah, you did. You said 3 from the quiz, 3 from the
Yep. So the test will get graded this weekend. I had some spot checking, looked at a few here and there, and they weren't that bad.
Straight lie.
He must have just looked at all the writing.
I'm sure about that.
You're looking at the answer key.
Yeah,
Have you been working on this?
not that bad.
This lab.
Is that coming on? Ignoring me. There we go.
You're supposed to print it off since you were in the or he was going to.
So, today, we are working on getting back to normal for the first time, really, right?
Should put that tab.
It's been a while. Feels like it's been a very long while since things have been sort of just normal. All right, Stacy. Ryan.
Here.
Chandrata. Stormy. Samantha.
Here.
Casey.
Here.
Rolanda.
Here.
Shelby.
Here.
Aquavius. James.
He just went to the radio.
Enrique.
Here.
Michaela.
Here.
Bren. Bren. I've now seen it and written down, and that helps. Bren. Coral.
Here.
Carly.
Here. Here.
Kelly. Joe. Dakota. Anna.
Here.
Carrie.
Here.
Robert.
Here.
Diamond.
Here.
You don't look at all like your picture.
What did he say?
Marjwan.
Here.
Dylan.
Yeah.
Tanisha.
Here.
Maisie. Anna. Justin.
Yeah.
Emily. Caitlin.
Here.
Chelsea.
Here.
Bailey.
Here.
Bernicia.
Here.
Shelby.
Here.
Colton.
Here.
Tony.
Here.
Colin.
Here.
There we go. All right. So, the Earth. Anybody familiar with the Earth?
No.
The blue.
Been there? It is the place to be. It is the place to be. So, you've seen the photos from space, right? NASA just released a new selfie of the Earth and the Moon, because they have right now they have a satellite out in space that's 1 million miles out, which is a good location to take a selfie of the Earth from, right? It's about 4 times as far away as the Moon. And the satellite's real purpose is to study the sun, and it's easier to study the sun if you can see it all the time, right? And so they stuck it way out, away from the Earth, so we could see the sun all the time. But it's still, occasionally they point it back at the Earth, catch some cool pictures. But we're all familiar with the Earth, we're all familiar with the fact that well, we'll get into, it is not exactly as it's always been. It's changed, right? Over long periods of time, it changes. The continents move around. The continents are still moving around. This is why we have some of the earthquakes we have. The continents are moving. They don't move fast. I mean, it's like, yeah. And that's like a whole year worth of moving. Yeah. But they're still moving. When something that big as a continent runs into something else, well, even if it's moving slow, that's a pretty big crash, right? All right. So, and we forget, because of the way we do our maps, we flatten out the Earth. If you look at, this is Africa, we forget exactly how big Africa actually is. Because it's near the equator, everything else looks bigger to it when you flatten, bigger relative to it when you flatten out the map, right? Africa's actually really big. It's easy to forget just how enormous it is. So, we have our atmosphere, which you guys should, I'll send you a link to the video cams coming off the International Space Station, because that's a great way to see just how thin a layer of air we live in, right? I mean, this from here to here, that's a little over 12 million meters, or 12,000 kilometers, right? 12,000 kilometers here to here, but the atmosphere is only about 150, right? So the atmosphere is this thin little layer on top of the globe. So we think of, well, we live in this whole big world. Actually, we live in this really thin little layer on top of the world, right? So it's shaped roughly like a ball because of gravity. All right, if you get out, if you pay attention to some of the smaller objects out there in space, they're not shaped like balls because they don't have enough gravity to force everything into a ball. It is slightly shorter from the middle to the top and bottom than it is across the equator. Why is that? Any ideas? It's because we spin.
Yeah.
Right? And when we spin, what happens when you spin? Your arms want to go out. Because your arms want to go out, right? You get a little bigger. Well, the Earth is spinning, and that makes everything in the middle go out a little bit. So it gets a little squat and a little wide. Right? Not by a lot. I mean, this is 6356 or 57 versus 6378. That's just, 20 kilometers. That's, Rosedale or Louisville, right? Not a long distance, but it's still a distance. So if we look at what the Earth is made of, we're not talking about the atmosphere, but we look at what the Earth is made out of. Oxygen, silicon, aluminum, iron, calcium, and magnesium. Right? This is why it's great when we can make things out of silicon. Why? Because we got a lot of silicon. It is cheap. It's everywhere. You get silicon in our rice stalks. Right? The reason rice stalks stand up straight and hold up is because they suck up silicon or silicates in order to construct the stalk and that makes them stiff so that the rice can stand up and you can have the seeds at the top high up out of the water. So silicon and oxygen usually occur together because they're bound up together chemically. And you're all familiar, who's been to the beach? Right? Almost all of that sand is silicon. Right? Most of the sand is silicon. You have glass in your windows at home, that's silicon. Right? It's great stuff. It's everywhere. Okay. So, the volume of a sphere. The volume of a sphere is 4/3 pi times the radius of the sphere cubed. Okay? So that's what's showing up in this when we talk about the density of the Earth. Density is mass per unit volume. If we take a cubic meter of air, right? Cubic meter of air, how much do you think that weighs?
A gram.
1.2 kilos, close to 3 pounds.
So nothing.
Well, a lot more than you expect, right? I'm always surprised when I look at the density of air. So if you take a cubic meter of air, right, 1.2 kilos. This is why when we get our cars up to speed,
How do they work this out?
Hmm?
How would you work that out?
there are various ways to work that out. We can do it. Right? When you get your car up to speed, you're spending most of your energy pushing that air out of the way. Right? That's what all your gas is going to when you're driving down the highway. It's pushing air out of the way. So we look at the density of the Earth. So we can get the mass of the Earth from the orbital dynamics, right? That was a couple of chapters ago. Get the mass of the Earth from the orbital dynamics, measure how big it is, and we can get the density. And density of water, 1 gram per cubic centimeter. Density of most rocks, 3 grams per cubic centimeter. Iron, 8 grams per cubic centimeter. But the average density of the Earth, 5.5 grams per cubic centimeter. Right? Water is 1 gram per cubic centimeter
Stop it.
by definition. Right? Because this is how we defined a cubic centimeter. Or it's actually how we defined a gram. Right? Define a gram as the amount of water you have in 1 cubic centimeter. So, Earth, more dense than ordinary rock, less dense than iron. That kind of gives you an idea of what's in the middle. So the core of the Earth is mostly iron. The core, the very middle, mostly iron. Have you ever taken a water balloon and just kind of poked it and watched the waves go around the water balloon? Right? So we've done that with the Earth, not poked it real hard, but we studied both with earthquakes and with machines what happens if we send a wave through the Earth. Right? Now, most of the waves we send are these transverse or compression waves, or they call them P-type waves. We'll get on the next slide. Okay. So we use waves that go through the Earth to get a picture of what's inside. Now, seismologists do this all the time. Geologists do this all the time for oil companies. I don't know if you've ever seen oil companies have these really big trucks, and they'll drive along and they'll set down this big thing in the middle, and they'll lift the truck off the ground and they go, right? and then they'll all go down the road a little bit further, and they'll put them down there. They're sending seismic waves through the earth, and they're measuring the reflections to use sound to get a picture of what's inside the earth. It's just like what we do with ultrasound when we look at babies inside of people, when we look at the heart, right? When we look at other organs inside of our bodies using ultrasound, we use sound to look inside the earth. We also use sound to try and get a good picture of what's going on, right, inside the earth. We also use sound to detect that the Soviets set off a nuclear bomb. Or the Chinese, or the Indians, or the Pakistanis, or the North Koreans. Right? Because a nuclear bomb sends a wave through the earth. And so we have detectors that detect those waves, and it's kind of like having a big microphone. So if you had a microphone and you had a microphone, and the two of you were comparing signals really well, and there was one other microphone in the room somewhere, you guys could compare signals and figure out where I was standing while I was talking. Right? And that's what we do with all of these microphones that we listen to earthquakes with, and we listen to nuclear bombs with, and we listen to other things with, you know. And some of the things that we listen to are things we actually do on purpose to try and create images using sound of what's going on. I don't know if you've ever seen, well, okay, you guys weren't contractors with the military for 16 years, so. But you'll see modern Humvees, there'll be one of them, usually the command vehicle, that has a set of 3 little black things sticking up. Those are microphones. And they use those microphones to tell them where a shot comes from, if it hears a shot. And so they immediately know the guy's over there, the guy's over there, right? Based on when the signals arrive at the microphones, they know where the shot came from. So there are 2 types of waves that happen in the Earth's crust. These actually are important in terms of what it does to buildings. One is called a P wave, which is a pressure wave. P wave is what happens when I talk to you. I speak and I push on the air, and that pushes on the next layer of air and pushes on the next layer of air, and that pressure wave makes its way out to you. It's way out to you and you hear me, right? An S wave is what happens when you wave a rope up and down. So earthquakes come in several, 2 main varieties. One is as a P wave, and the other is as an S wave. An S wave is worse for buildings, right, than a P wave. A few years ago in Virginia, I was on the phone, and I felt an S wave go through, sitting in my office and talking to somebody, and I felt, boom, you know, an S wave goes through, and I talked to the guy and said, hey, we just had an earthquake. He's like, right, really? And we're talking about it, and then he goes, whoa, it just came here. Like, okay, so it's between you and me, but closer to me, right? And we had one other person say out in West Virginia on the phone, we would have been able to zero in on where the earthquake was a little better based on the timing. So S waves, the earth goes up and down, right? P waves, it's just pressure. It's just pressure. So this is just pointing out that if you're opposite to where the earthquake happened, all you're ever going to see are P waves, because the S waves aren't going to make it through. The S waves get blocked, right? The S waves get blocked by the liquid core. So we have our mantle, which kind of floats on top of a liquid core, and then in the middle there's some iron. Right? So we have, best we can tell, we've not actually drilled down and taken a look because we can't, right? But as best we can tell, we've got an iron core surrounded by liquid, right? This is rock that's simply so hot that it's always liquid. Surrounded by the mantle, The mantle is sometimes pretty hot, and then there's the crust, which is what we live on, right? Just a thin, pretty thin little layer. So the crust, 12 to 43 miles deep, and then that's about 3,000 kilometers. That's a couple thousand kilometers, and 1,200 kilometers for the iron core. A lot of iron. A lot of iron. So, denser stuff goes to the middle. Why? Gravity's pulling everything in, right? And so the denser stuff works its way down to the middle. That's why the iron is at the middle. And lighter stuff ends up on the top. The inner core, if the iron core is surrounded by molten lava, molten rock, right? Why is the inner core solid? It's solid because gravity is strong enough that even though it's hot enough to be a liquid, it's not. Because gravity holds it together, right? Gravity keeps it from melting. Yeah. It's just an example of, same thing happens with ordinary stuff, right? Chocolate chips always end up at the bottom because they're denser. Same thing happened with the earth. The denser stuff slowly made its way to the middle. So, earth core, 6,500 Kelvin. Pretty hot, right? Some of it's leftover latent heat from when we were put together. And when things were crashing all over the place. Because the solar system used to be much more crowded with debris, and that debris slowly collected into planets. Right? Solar system much, we've got the asteroid belt out there. We haven't really talked about it yet. Got the asteroid belt out there. It used to be more like that all the way up to the sun. A lot of rocky stuff all over the place, but as those pieces, we'll cover this later, as those pieces collected together, they started forming planets, and that would pull in more, and as you pull in these pieces, you have collisions, and that heats things up. The other source, though, is normal radioactive decay from the naturally occurring radioactive elements that are all over the place. If it were even just 50 years ago in the American Southwest, you would be probably putting yourself in a dangerous position by buying some of the native artwork if it had yellow paint in it. Because in the American Southwest, they used to use uranium because it makes a nice yellow paint. And it took us a while to figure out the yellow paint's not a good thing, it's uranium. And people were buying nice little pitchers and things like that they would bring back and put orange juice in and water in. And the natives there didn't know that it was uranium. It was just the material that made nice yellow paint.
Did it affect them?
Oh, it did. It did. So, no matter which source the energy is coming from, it takes a while for it to get out. The Earth is slowly cooling, but it's going to take a long, long time for the core to cool off enough to matter. Okay, so, radioactive elements. The radioactive elements are how we figure out how old things are. Because we can measure, potassium's a good one, we can measure how long does it take for radioactive potassium to decay? And so there's something we call the half-life, right? The half-life is how long it takes for half of the potassium to decay. Now, it keeps going. If I have, suppose I had 10 kilograms of potassium. Does it have the half-life on here? Yeah, 1.28 billion years. Okay. In 1.28 billion years, that 10 kilograms of potassium will be down to 5 kilograms of potassium plus other stuff, right? How long till I get 2.5 kilograms? Or in another 1.28 billion years, would I have 0? No. So in another 1.28 billion years, I have 2.5 kilos. So the half-life is how long it takes to lose half of whatever you have. Right? That's what the half-life is. In one half-life, half the material will be gone. In another half-life, half of what's left will be gone. In another half-life, half of what's left will be gone. Does that make sense? Right? It's not linear, it's an exponential decay. Right? You never get to 0 in any realistic sense. So we use this to say how old the Earth is. And we look back and say, you know, at one point, all of this stuff, the potassium, the calcium, and argon, started out as potassium. And we work our way backwards to say, if we work backwards, how old is the Earth? And we get to about 5 billion years. Was when it finally kind of solidified into a ball-like object that was all hot and molten and stuff like that. This is how we also, well, let me say a little bit more. So when potassium decays, it decays into calcium and argon, right? And so it's by looking at this mixture we know how far back to go to get to where we started. One of the things we get because of the, well, let me say, when we're talking about earthquakes, earthquakes happen up here in this little crust. That's where we are up here. But beneath us, because of all the heat, the mantle moves around, right? There are convection currents, things move. Occasionally this pokes up through the crust and we get what? Volcanoes, right? Occasionally it pokes up through the crust and we get a volcano. I still need to go to Hawaii to see the volcano there. Anybody had a chance to go? Did you like it?
Pretty cool.
Pretty cool. So this same convection happens when we cook, right? You know, yesterday I was cooking grits. You can see all the convection from the grits. You know, they get hot on the bottom, they bubble up, cool off, and that keeps going, right? The hot ones on the bottom bubble up, come to the top, and the cooler ones sink back down. When these convection currents collide and they're both like lifting up, we get these little rifts, right? And this is where, when we get these, they're adding to the crust here. So again, like the grits, bubbles up in the middle, and the cool ones start spreading out from there as new hot ones are added. And so we get these rifts in the ocean where new material is being added to the crust and it creeps out from there.
It's giving us more earth, but
Well, somewhere else, it's going down, okay? So we're not getting more surface to play with, we're just trading, we're getting some new here, we're losing some there. And so it takes a long time, right? We don't notice these things, but somewhere else, we have stuff going underneath and going back down, you know. So, but these are really slow movements. We're talking about, you know, a centimeter a year. So it's not very fast. You have to pay close attention to really notice. We believe there's a point where what we have as continents today were all one big mass. Right? It's all one continent. And it slowly drifted apart. And we believe it was one big mass over here because, you know, the Pacific Ocean is big. I don't know if you ever really pay attention to a globe, but the Pacific, that's a big body of water. That's a long stretch without really anything in it at all. So our modern continents, and you can even kind of see how, yeah, it makes sense, these fit there, right? And so this is all part of these just kind of slowly breaking apart. This shifting around of the crust we call plate tectonics. So we think of the little pieces as plates. Right? We have a plate here, plate there, and they move against each other, they move under each other, they move over each other. And so that's plate tectonics. This is another picture of how we think things may have evolved with more ocean, and then the ocean, and then land sort of rises up out of the ocean until we finally get to where we are today. In some places like the Himalayas are still rising, right? So every year when someone climbs Mount Everest, they set a new record because it's a little taller than it was the year before, right? All right. You know the Earth has a magnetic field, right? You know, well, you probably don't know that magnetic north and true north. True north is what? What's true north? True north, if you went to true north, you'd be standing at the spot where the Earth is spinning around you, right? You'd be right on the axis that we're spinning on, right? You wouldn't notice the spin, but you'd be right on the axis that we spin on. If you step off a little bit, you know, you'd be going in a little circle during the day.
So the North Celestial pole?
Mm-hmm.
Okay.
Yep. Right? So if you stood exactly on the North Pole over a day, you'd turn a full circle. Right? You wouldn't notice, other than the sun, depending on where the sun was. If you were there at the right time of year, you just watch the sun go in a circle around you. All right? If you step off a little bit, then in a day, you're going in this little bitty circle. So true north, which is the celestial pole, and magnetic north are not exactly in the same place. The reason is, in the mantle and in the lava, the liquid rock underneath the mantle, there are currents that are actually causing us to have the magnetic pole. All right? So those currents actually change a little bit, and so magnetic north moves a little bit all the time. Not a lot, but a little bit. Although it has on occasion completely flipped, right? So that magnetic north would be on the South Pole. So sometimes, and if it ever happens, there'll be Boy Scouts everywhere panicked because their compasses will suddenly be, pointing the opposite direction. But it has flipped in the past. Well, this has real life implications if you're using a compass trying to go somewhere and you don't adjust for the fact that true north and magnetic north are not one and the same. So what you do is you can actually calibrate a compass so that here in Cleveland it points to true north by just setting things off a little bit so that when it's pointing to magnetic north, it's pointing to where, because the compass points to magnetic north. When it points to magnetic north, it's actually pointing in the right angle away from true north so you know where true north is, right? So you can change your compass a little bit. This actually has real, this is actually part of a real life problem. Have you ever noticed the border between Mississippi and Alabama has this slope here and then a kink and goes straight south? The border was supposed to go straight south. And Mobile, Alabama would be in Mississippi. But the guys doing the surveying were from New Jersey and they forgot they had to correct their compasses for down here. And so they were following their compass along a line that they thought was north-south that wasn't. And then they got here, and I don't know exactly what they said, but it probably wasn't pretty. And they adjusted their compass and they went straight south. Now, they're lucky I wasn't the guy that had their contract, because I would a little bit harder about things like this, and I would have said, well then you need to go back up here. And you need to start over. Right? I have no idea. I have no idea. But because of their mistake, Mobile, Alabama is in Mobile instead of being Mobile, Mississippi. So this difference can have an effect, right, if you move over long distances. You can calibrate it for a local area, and it's okay. Our magnetic field is actually a wonderful thing. And it is a big part of why it is safe to be as close to the sun as we are. Right? Because the sun sends out charged particles all the time. And there's just a constant stream of them. And what the magnetic field does is they hit the magnetic field and it sends them in curves towards the north and south pole. So these charged particles then, instead of coming straight in and hitting us here in Cleveland, a lot of them do, but a bunch of them get diverted, right? Instead of coming here and just hitting us straight on, they go around and they go to the North Poles and the South Pole. And there they create what? What do we have at the North Pole everybody talks about? Aurora Borealis. The Aurora Borealis is these charged particles coming in and hitting the atmosphere. Right? Oh, I meant to, I will send myself a note real quick. The Aurora Borealis creates it creates electromagnetic waves that are down in the very long wavelengths, that are down in the audio range. And so there are people that have they've gone up into Finland and Canada to farms and hooked up to fences, because you need a really long antenna. So they hook up to a fence and they would record the aurora borealis. Right? And you can hear all these little buzzes and whistles and clicks and right? So I will send a link out to you guys to the sound of the aurora borealis. And so if you want, you can listen to it and just see what that sounds like. This is all the charged particles from the sun hitting our atmosphere at the North Pole. So this is a great thing it does for us, and it ends up, we end up with what are called the Van Allen belts, which are layers where, because of these particles coming in, they're layers of charged radioactive particles, right, that are up there that you have to go through when you go into outer space. There was a big debate back before we went to the moon about would it kill the astronauts when they went through the Van Allen belt and all that kind of stuff. Just like there used to be a big debate about whether or not you would die and suffocate on a train moving at 30 miles an hour. We've had a lot of debates like this over the years, right? Because they used to think if you went faster than a horse could run, you'd suffocate because you wouldn't be able to run, be able to breathe. This is one of the arguments against trains and cars. We used to worry that the Van Allen belt would fry you as you went through. Well, that doesn't happen. And when we get to the sun, we'll find out the sun does the same thing. The sun has its own big magnetic field. And when people argue about has Voyager 1 left the solar system or not, they're kind of arguing about, are we outside of the magnetic sphere? Are we outside of the Oort cloud? How far away have we gotten? Because there are different places you could call the edge of the solar system, right? And there are people who are saying, hey, it's now moved outside of this envelope of the magnetic field of the sun. We should say it's that the Voyager 1 is now out of the solar system. And other people saying, well, no, it's still inside the Oort cloud, which is all this stuff loosely held to our star that's still out there circling our star. So, you know, it's not outside of that yet. So we can slice that a number of different ways. But the sun has a magnetosphere just like we do. The aurora borealis, right? Charged particles streaming in. And they're streaming in and they're doing what? Why does it make light? They're streaming in and they're hitting the electrons on the atoms in the atmosphere and making them go to a higher energy, and when they come back down, they emit light. Right? This goes back to the atomic spectra we talked about a couple of chapters ago. Right? They're exciting those electrons, and then when electrons go back to their ground state, they send out light, and that's the light we see. It's another thing I have to go see. All right? Not seen the aurora borealis. I need to do that. How many of you looked at the pictures of Pluto in the recent flyby we did? Okay. Very exciting for me. All right. There, you got to see that Pluto had a very thin atmosphere, right? We don't think of, our atmosphere is not all that thin. It's not nearly thick as, say, Venus's, but our atmosphere is not all that thin. But we have to remember, it is pretty thin compared to what we think of, right? I mean, our atmosphere is 150 kilometers. So by the time you drive to Biloxi, if you were going straight up, you'd be well outside the atmosphere. So it's not that thick, right? It's really not that thick. It's this little thin layer. And we can't even live in most of that. We can only live in the bottom, really the bottom 10 kilometers? No, not that high. The bottom 3 kilometers, right? We can really only live in the bottom 3 kilometers. Once we get above that, we have to take air with us to breathe. So So we live in this really thin little layer. This is why when people talk about, well, the Earth is so big, you know, how can we affect it? Well, it's this really thin little layer, right? That's where we live. So it really gets, in terms of language, right? We divide it into troposphere. Troposphere roughly translates into, I can read that, right? And stratosphere, which is, I can't read that. So, and then where the edge of space is kind of depends on how long you want your satellite to stay up. All right, because a lot of satellites are up there at only about 250 kilometers. They will eventually hit enough air that they'll come down, but they'll stay up for 20, 30 years. All right, they'll stay up for a long time.